Welcome to the 9th lecture in abstract algebra. The topics that we'll explore in this lecture include magmas, semigroups, monoids, and an introduction to homomorphisms and isomorphisms. Okay, so recall that in the last lecture we looked at a very basic binary algebraic structure called a magma, which consists of a set S closed under a binary operation which we denote with the symbol star. Recall that to indicate that it is a structure, we group the set together with its operation enclosed in angular brackets. Now in this lecture we're going to begin to look at more complicated structures based on additional properties that the binary operation may have, or whether or not the underlying set contains certain elements. So a magma is a set together with a binary operation defined on the set S. And recall that this implies that the closure property for the binary operation. So also recall that the binary operation star is a function mapping ordered pairs of the set back into itself. So in a magma, the binary operation has the property of closure. There are additional properties that we would like a binary operation to have, and these include the commutative and associative properties. So a binary operation star defined on a set S is commutative if and only if for every pair of elements A and B in the set S, it does not matter the order in which we perform the operation. So in terms of the function phi, this means that the phi of the ordered pair AB is the same as phi of the ordered pair BA. A binary operation star defined on a set S is associative if and only if for every three elements A, B, and C in S, it does not matter how we group the terms. A star the quantity B star C is the same as quantity A star B star C. So in terms of the function phi, we have that phi of the ordered pair A phi of BC is the same as phi of the ordered pair phi of A, B, and C. Right? Okay, so now we define a new structure, a semigroup. Is a magma with associativity. That is, the operation star in the magma is associative over the set S. So let's look at some examples. First, an example of a magma that is not a semigroup. The set of complex numbers together with the operation star, where star is defined by Z1 star Z2 is the product of Z1 with the conjugate of Z2. The structure is a magma, but is not a semigroup. Okay, so proof. Let Z1 and Z2 be complex numbers. Then the product Z1 star Z2 is the product of two ordered pairs, x1, y1, with the conjugate of x2, y2. This is the product of the ordered pair x1, y1 with the ordered pair x2 minus y2, or negative y2. This gives x1 times x2 plus y1 times y2 as the real part, and x2, y1 minus x1, y2 as the imaginary part. But this is a complex number. And so the set of complex numbers is closed under the operation star, and hence the structure consisting of the complex numbers together with this operation star is a magma. So now we look at whether or not the operation is associative over the complex numbers. So let Z1, Z2, and Z3 be complex numbers. Then Z1 star the quantity, Z2 star Z3 is Z1 times the conjugate of the quantity, Z2 star Z3. This is Z1 times the conjugate of Z2 times the conjugate of Z3. This gives us Z1 times the conjugate of Z2 times the double conjugate of Z3. So this gives us Z1 times the conjugate of Z2 times Z3. So now we look at the quantities Z1 star Z2 star Z3. This gives us Z1 star Z2 times the conjugate of Z3. So this gives us Z1, the quantity Z1 times the conjugate of Z2 times the conjugate of Z3. And so this is Z1 times the conjugate of Z2 times the conjugate of Z3. Now, in general, Z1 times the conjugate of Z2 times Z3 is not equal to Z1 times the conjugate of Z2 times the conjugate of Z3. And so the operation star is not associative. Over the set of complex numbers. And so the structure consisting of the complex numbers together with this operation star is not a semigroup. Okay, so next we'll look at a structure, a magma, that is a semigroup. The structure consisting of the set of positive integers together with addition is a semigroup. So proof. Let A and B be positive integers. Then A and B are integers such that A is greater than 0 and B is greater than 0. And so the sum a plus b is an integer such that a plus b is greater than 0. And hence the product a plus b is in the set of positive integers. And so the set of positive integers is closed under normal addition. And thus the structure consisting of the set of positive integers together with normal addition is a magma. Now for every 3 elements, A, B, and C in the set of positive integers, it does not matter how we group those terms. When we perform a sum, we always obtain the same result. And so the operation of addition is associative over the set of positive integers. And so the structure consisting of the positive integers together with normal addition is an associative magma and is therefore a semigroup. All right? So now we define a new term. Let the set S be a subset of the set T, and let the structure consisting of the set S together with a binary operation star be a magma. The identity element for the operation star is the element which we denote with the symbol E in the set T, such that for every element A in the set A, E star A is the same as A star E, which gives the element A. So notice that the identity element is dependent upon the operation, that a magma may or may not contain the identity element, and that multiplication, or rather that performing an operation with the identity element is commutative. Now, it is not necessary that the operation be commutative over the entire set, but the identity element and any element of the set commutes. All right? So notice that I said the identity element, indicating that there's only one. We need to now prove that. A magma S star has at most one identity element. So proof. Suppose that E and E prime are both identity elements. For the operation star. Then, regarding the element E as the identity, we have E star E prime gives that other element E prime. Now, regarding E prime as the identity, we have E star E prime gives that other element E. And so the element E is equal to E star E prime, which is equal to E prime. And so E is equal to E prime. So a magma has a unique identity element for the operation in the structure. So now we can define a new structure. A monoid is a semigroup with identity. That is, the underlying set in the semigroup contains the identity element for the operation star. So let's look at an example first of a semigroup that is not a monoid. The semigroup consisting of the set of positive integers together with normal addition is not a monoid. So let E be the identity for the operation of addition. Then, for every element A in the set of positive integers, we have that E plus A is the same as A plus E, which is that element A. Notice that E plus A equals A implies that E is the number 0, and 0 is not in the set of positive integers. So the set Z superscript plus, that is the set of positive integers, which means more than simply non-negative, does not contain the identity element for the operation of addition. And so the semigroup consisting of that set under addition is not a monoid. All right. So this structure fails to be a monoid because it does not contain the number 0. So we'll look at an example of a semigroup that is a monoid. Let the set S be the union of the positive integers together with the singleton set containing the number 0. That is, we're adding the number 0 to the set of positive integers. Then the structure consisting of the set S under or with the operation of addition is a monoid. So proof. Let A and B be elements in the set S. Then A and B are integers such that A is greater than or equal to 0 and B is greater than or equal to 0. And so the sum A plus B is an integer such that A plus B is greater than or equal to 0. That is, the sum A plus B is in the set S. And hence, this set S together with addition is a magma, as it is closed under the operation of addition. So now we look at associativity. for every three pairs of, or for every three elements, A, B, and C in the set S. As before, with simply the set of positive integers, it does not matter how we group the terms. We will obtain the same result when we take a sum. So the operation of addition is associative over the set S. And there exists the number 0 in the set S such that for every other element A in the set S, we have that A plus 0 is the same as 0 plus A, which equals A. So the set S contains the identity element for the operation of addition. Therefore, the structure consisting of the set S together with addition is a monoid. All right.